This is a tutorial on conic sections in polar coordinates. Whenever we deal with conic sections in polar coordinates, we have to deal with this term called eccentricity. Now, eccentricity is usually represented with an E. But don't get it confused with the natural constant where E is equal to 2.71. We're dealing with a different E when we talk about eccentricity. Now, eccentricity, that is the ratio of two distances. Every conic section, whether it's a parabola, an ellipse, a hyperbola, a circle, it doesn't matter, every one of them has at least one focus, and every one has at least one directrix. Now, we don't usually solve for directrix when we're dealing with ellipses or hyperbolas. It's something we only found when we dealt with parabolas. Eccentricity is the ratio of two distances. One is the distance between our focus and any given point on a conic section. The other distance is the distance between that same point and that conic section's directrix. Now we know when we deal with a parabola that the distance of every point on our parabola is the same between the focus and the directrix. So if these two distances are the same, that would mean that the eccentricity for a parabola is always equal to 1. Now again, we didn't usually find a directrix for an ellipse or a hyperbola, but what's important to remember that if you have an ellipse or possibly a circle, it has an eccentricity that is some positive fraction between 0 and 1. And if your eccentricity is greater than 1, that means you have a hyperbola. Now remember, the eccentricity is just the ratio of the two distances, but once you understand that, we're just going to use this number to identify what type of conic section we're dealing with. Now, every conic section in polar coordinates has one of two basic equations. It's either r is equal to e times d over 1 plus or minus e cosine theta, or r is equal to e times d over 1 plus or minus e sine theta. Both of these equations assume that one of your foci, or your focus, is at the origin or at the pole, because we're talking about polar coordinates. Now, if you have an equation that has a cosine in the denominator, that means that your directrix is a vertical line. And if your directrix is a vertical line, that means your horizontal axis of symmetry is your major axis of symmetry. If you have a sine in the denominator, that means you have a horizontal line as a directrix, and your major axis of symmetry is vertical. So if we had a parabola, and that equation of our parabola had a cosine in the denominator, that would mean that we would have a vertical directrix, which means it has the equation x is equal to some number. It also has a horizontal major axis of symmetry. So if the major axis of symmetry is horizontal, that means your parabola opens in the horizontal direction, so either the positive x or the negative x. If the equation of our parabola has a sine in the denominator, that means it has a horizontal directrix, which means it would have the equation y is equal to some number, and a vertical major axis of symmetry, which means it's going to open in the positive or negative y direction. So cosine means x and sine means y. Now this e term, this is our eccentricity. So just by looking at this e term, we can tell if this equation is representing a parabola, a circle, an ellipse, or a hyperbola. The last thing we have to talk about is this d term. This d term is the equation of our directrix. If d was equal to 4, then our directrix is either the line x is equal to 4 or x is equal to negative 4. The way to determine whether it's positive or negative is to look at this plus or minus in our equation. If this is 1 minus e cosine theta, then your directrix is x is equal to negative 4. If this was 1 plus e cosine theta, then your directrix would be x is equal to positive 4. So d tells you the number, and then whether this is plus or minus, that tells you whether that number is positive or negative. And the same thing works for a horizontal directrix. This is still y is equal to d, or y is equal to negative d, and whether it's positive or negative is determined whether this is positive or negative. Well, that's a lot to take in. So let's try an example here. We have a conic section, and its equation is r is equal to 4 over 1 minus cosine theta. It's a cosine, which means we're not going to use this sine equation. We're going to use this cosine equation. We have a 1 here, and we have a 1 here, which means this is in standard form. In front of my cosine, I have a 1, which means my eccentricity is equal to 1, because this is 1 plus or minus e cosine theta, and we have 1 minus cosine theta. So you can assume a 1 out front, and that means e is equal to 1. And if our eccentricity is equal to 1, that means that this is the equation of a parabola. Now if e is equal to 1, realize that this e times d has to be equal to 4. So if e times d is equal to 4, that means d is equal to 4. Now this is a cosine theta, which means our parabola is going to open in either the positive or the negative x direction. It also means that our directrix is going to be a vertical line. So our directrix is going to have the equation x is equal to d, which is 4. But this is a minus sign in our denominator, so actually our directrix has the equation x is equal to negative 4. So let's try graphing this. We know our directrix is x is equal to negative 4. We know this is cosine theta, and our eccentricity is equal to 1, so this is a parabola. We know when we use these equations, we have a focus at the origin or at the pole. And since my directrix is x is equal to negative 4, I can graph that. That would look something like this. Now, if my focus is at the pole or at the origin, and this is my directrix, then halfway between these would be my vertex. Well, if this is x is equal to negative 4 and this is 0, 0, then halfway between there would be right here. So this is my vertex. I know because this is a cosine in the bottom that my parabola has to open in either the positive or negative x directions. But since my directrix is here and my focus is here, that means my parabola is going to be opening in the positive x direction. Now to graph this, the last thing I need is a couple of points. I'm going to choose some values of theta and solve for r. So values of theta that I'm going to choose, well, I'm going to pick 90 degrees and 45 degrees. We'll start with those. If I plug in 90 degrees in for theta, I'll have r is equal to 4 over 1 minus the cosine of 90 degrees. Now the cosine of 90 degrees, this is equal to 0. So I'm left with 4 over 1, or r is equal to 4. So when theta is 90 degrees, r is equal to 4. I go along the 90 degrees, or the positive y-axis, up 4, and I'll get to a point right there. Now this is symmetrical across our polar axis, or you can think of our x-axis, which means I'm going to end up with another point right here. This is the point 4 and 270 degrees. And if you plug in 270 for theta, again you'll get 0 because the cosine of 270 is 0. 1 minus 0 is 1, and once again you'll end up with 4. Next I'm going to plug in 45 degrees, so I'll get r is equal to 4 over 1 minus the cosine of 45 degrees. Now the cosine of 45 degrees is equal to the square root of 2 over 2. So I have r is equal to 4 over 1 minus the square root of 2 over 2. If you plug all this into your calculator, you'll find out that r is about 13.7, which is way off our grid. This is about 9, so it'd be out here somewhere. And of course it's symmetrical, so you'd be out here again. Let's try one more point. What happens if we plug in 0 for theta? If I plug in 0 for theta, I'll have r is equal to 4 over 1 minus the cosine of 0. Now the cosine of 0 is equal to 1, so you have r is equal to 4 over 1 minus 1, or 4 over 0. Can never divide by 0, so this is undefined. That means there is no points in the 0 direction, which would make sense because this is a parabola. Now if I connect these points with a smooth curve, our parabola should look something like that. Now sometimes you'll ask to graph a conic section in polar coordinates, but you're not actually given the equation. Here we're told that our focus is at 0, 0. It's at the pole, or you can think of it being at the origin. We're told we have an eccentricity equal to 2. This tells us right away, because this is greater than 1, that we're going to be graphing a hyperbola. Now our directrix is y is equal to negative 4. If it's y is equal to, that means this is a horizontal directrix. And since it's horizontal, or y is equal to, we're going to be using the sine equation. Sine means y. So if we're going to be using this equation, r is equal to e times d over 1 plus or minus e sine theta. Now we know e. E is 2. So r is equal to 2 times d over 1 plus or minus 2 sine theta. Now our directrix is the line y is equal to negative 4. So that means 4 is going to be d. And since it's negative, that means this is going to be a minus. So we have r is equal to 2 times 4 over 1 minus 2 sine theta. Or to simplify this, we have r is equal to 8 over 1 minus 2 sine theta. So this is the equation that we're going to be graphing. So let's try graphing it. Remember, it's r is equal to 8 over 1 minus 2 sine theta. The focus is at 0, 0, or it's at the pole. The directrix is the line y is equal to negative 4. So that's our directrix. Although, again, we're graphing a hyperbola here because our e is 2, it's greater than 1. And we don't usually use our directrix when we graph a hyperbola. So instead, let's find some theta values and solve for r. So theta values that I'm going to choose, well, this is a hyperbola that's going to open in the y directions. So I'm going to choose 90 degrees, I'm going to choose 270 degrees. I also may try 0 and 180. So let's start with those. If I plug in 90 degrees for theta, I'll have r is equal to 8 over 1 minus 2 sine 90. Now the sine of 90, that's equal to 1. So what I have here is r is equal to 8 over 1 minus 2. That means I have 8 over negative 1, or r is equal to negative 8. So if I go to the 90-degree mark, and then negative 8 would mean down 8, we'd have a point right there. If I plug in 270, I'll have r is equal to 8 over 1 minus 2 times the sine of 270. The sine of 270 is equal to negative 1. So I have r is equal to 8 over 1 minus 2 times negative 1. And that means we have 8 over 3. Well, that's 2 2/3. So that would be right about here. Next, we're going to plug in 0 for theta. So we'll have r is equal to 8 over 1 minus 2 times the sine of 0. The sine of 0, that's 0. So we'll have r is equal to 8 over 1, because 2 times 0 is just 0. So 1 minus 0 leaves us with 1. So when theta is 0, our r is a positive 8. And we can plot that point. It's right there. Now we'll plug in 180. So r is equal to 8 over 1 minus 2 times the sine of 180 degrees. The sine of 180 degrees is also 0. So once again, our r value is equal to 8. And if we plot that point, we go along the 180 degree direction to 8, which should put us right there. I can kind of see how this is developing. Remember, this is a hyperbola that opens in the positive and negative y directions. And that means our hyperbola should look something like this. So let's graph one more example problem. Here we have r is equal to 6 over 2 minus the sine of theta. Now we have a sine here, which means this is going to be in the form r is equal to e times d over 1 minus e sine theta. Except this equation here is not in standard form, because this is not a 1, this is a 2. So instead what we're going to do is reduce everything by 2. Or you can think of multiplying both the numerator and the denominator by 1/2. If I do that, I'll end up with r is equal to 3 over 1 minus 1/2 sine theta. This equation is now in standard form. And now that it's in standard form, we can find out many things about what we're graphing. First off, my e term, that's equal to 1/2. If e is equal to 1/2, that means that this is an ellipse. Now that I know this is an ellipse, I can look at this sine term. Sine means y, which means the major axis of my ellipse, which is the longer axis of my ellipse, that is going to be in the y direction. So my ellipse is going to look something like this. I can also find my directrix, find my value of d, but because we're dealing with an ellipse, I really don't have to find that. Instead, I'm just going to pick several values of theta, plug them into my equation, and solve for r. So I create my chart. I'm going to put in values of theta and solve for r. I'm going to pick 0, 90, 180, and 270. I know this is an ellipse. I know one of the foci of my ellipse is going to be at the origin. which means I should have points in all four directions. So if I plug in 0 first, I'll have r is equal to 3 over 1 minus 1/2 sine of 0. Now the sine of 0 is 0. 1/2 times 0 is 0. 1 minus 0 is 1, so r is equal to 3 over 1, or you can just say it's equal to 3. If I plug in 90 degrees, I get r is equal to 3 over 1 minus 1/2 sine 90. The sine of 90 degrees is 1. 1 times 1/2 is 1/2. 1 minus 1/2 is 1/2. So we have 3 over 1/2. And that's equal to 6. If I plug in 180, I'll have r is equal to 3 over 1 minus 1/2 sine 180. The sine of 180 is 0. 1/2 times 0 is 0. 1 minus 0 is 1. So again, I have 3 over 1, or 3. If I plug in 270, I'll have r is equal to 3 over 1 minus 1/2 sine of 270. Now the sine of 270 is negative 1. Negative 1 times 1/2 is negative 1/2. 1 minus a negative 1/2, that's the same as adding, so it's 1 plus 1/2. So what I really have here is 3 over 1 and 1/2, or 3/2. This is equal to 2. So I can plot these 4 points. The 0 theta direction is the positive x direction. Go out 3. That's right there. 90 degrees is the positive y direction, so we go up 6, which is right there. 180 degrees is the negative x direction, and we go out 3, so right there. And then 270 and 2, 270 is the negative y direction, and 2 would put us right here. And that means our ellipse should look something like this. Now, if you couldn't see that, you could always plug in more values of theta and solve for r, and you could find these points as well. But to graph this ellipse, we first had to put this equation in standard form. Otherwise, we wouldn't have realized that it was an ellipse. And then once we do realize, we just plug in values of theta and solve for r. Now the last thing we're going to have to do in this section is convert conic section equations, which are in polar coordinates, into rectangular equations. Now here I have r is equal to 6 times the cosecant theta divided by 2 times the cosecant theta minus 4. You'll notice that this is not in standard form. I have a cosecant in the numerator and the denominator. Now the first thing I want to do is put this in standard form. So remember, cosecant, this is the same as 6 times 1 over the sine of theta divided by 2 times 1 over the sine of theta minus 4. Because cosecant is just 1 over sine. Now if I want to put this in standard form, I just multiply both the numerator and the denominator by the sine of theta. If I do that, this will cancel with this, and this will cancel with this. So I'll be left with 6 is equal to 2 minus, now when I multiply the denominator by the sine of theta, I have to distribute. So those cancel, but I still have 4 times the sine of theta. Now this is almost in standard form, except this isn't a 1, so we have to reduce everything by 2, or you can think of that as multiplying by 1/2 over 1/2. So we're back to r is equal to 3 over 1 minus 2 sine theta. This is the equation of a hyperbola, because our eccentricity here is 2, or greater than 1. Now that I have my equation written in standard form, I want to convert this into rectangular coordinates, or x and y coordinates. And to do that, I have to remember that x is equal to r times the cosine of theta, and y is equal to r times the sine of theta. Now the first step to doing this is taking this denominator and multiplying both sides by it. If I do that, I'll have r times 1 minus 2 sine theta is equal to 3. Then I'm going to distribute this r inside the parentheses. So we'll have r minus 2r sine theta is equal to 3. Now if you'll notice, this r sine theta, that's equal to y. So I have r minus 2y is equal to 3. Now I'm almost there, except I still have this r that I have to replace, but it's not multiplied by the cosine or the sine of anything. Well, we can also remember that r squared is always equal to x squared plus y squared. So what I'm going to do is add 2y to both sides, and we'll have r is equal to 2y plus 3. Now I'm going to square both sides, and I'll have r squared is equal to 2y plus 3 squared. Then I'm going to replace this r squared with x squared and y squared. So I'll have x squared plus y squared. That's equal to 2y plus 3 all squared. Now I want to FOIL out this right-hand side, so I'll have x squared plus y squared is equal to 4y squared plus 12y plus 9. Next, I'm going to subtract y squared from both sides. So I have x squared is equal to 3y squared plus 12y plus 9. Our next step is to complete the square with these y's, because I have this linear term here, 12y. So what I'm going to do is factor out a 3, greatest common factor, from both of these terms. So we'll have x squared is equal to 3 times y squared plus 4y, and then plus 9. Now to complete the square inside these parentheses, I have to add 4. But really, if I'm adding 4, this 4 is multiplied by the 3 outside. So I'm adding 12 to this right-hand side. And if I add 12 to this right-hand side, I have to add 12 to the left-hand side. So I'll have x squared plus 12 is equal to 3 times y squared plus 4y plus 4 plus 9. Inside these parentheses, I can factor that into a y plus 2 squared, still multiplied by 3, still adding 9. Now I'm trying to put this in the standard form of a hyperbola. So I'm going to subtract 12 from both sides. I'm also going to subtract 3 times y plus 2 squared from both sides. If I do that, I end up with x squared minus 3 times y plus 2 squared. That's equal to a negative 3. Now I'm almost there, except when we have the standard form of a hyperbola, this right-hand side is always equal to 1. So I'm going to divide everything by negative 3. Once I've done that, I'll have x squared over negative 3 plus y plus 2 squared over 1 is equal to 1. And then I'm going to just rearrange this. This is y plus 2 squared over 1 minus x squared over 3 is equal to 1. And that is our standard form equation with x and y coordinates of our hyperbola. So now that we've converted from polar to rectangular coordinate equations, That completes the tutorial on conic sections and polar coordinates.